sig figs, or significant figures. How to record the correct number of digits in your calculations. The number of sig figs depends on the measurement tools that you use. On the bottom scale, only the whole number is recorded. So the red line is somewhere between 2 and 3. We estimate it to be around 2.5, but it might be a little higher, it might be a little lower. The top scale has the tenths place marked, so we can do better than 2.5. We estimate it to be halfway between 2.5 and 2.6. We'll call it 2.55. But in this case, it's all right if we're a little bit off on that last decimal. It could be 2.56. It could be 2.54. We estimate the measurements to one place past the markings on the scale. To have good precision, you have to pay for it. For $99, you can buy an electronic balance that can weigh an apple, a coin, or a bug, all to the tenth of a gram place. But for $1,640, you can buy an electronic balance that can weigh an apple, a coin, or a bug to 4 places past the decimal. This is a much more precise measurement with many more sig figs in the measurement. It's expensive to buy tools that will measure more sig figs. So when we're able to measure with a lot of sig figs, we should not round those measurements off. Why do we care about sig figs? Sig figs are the number of digits that contribute to the precision of a number. In the number 40.5 grams, how many sig figs are there? Answer, all of them. They're all sig figs because all 3 of those digits contribute to the precision of the measurement. So we'd say there's 3 sig figs. The only digit that's ever in doubt is the digit 0. Sometimes they are and sometimes they're not. So how many sig figs are in the measurement 0.005 kilograms? In this case, only the 5 is significant. The zeros tell us it's a small number, but they don't help make it a better number. What about the number 0.0050 kilograms? In this case, again, the zeros on the left do not contribute to the precision of the measurement, but the 0 after the 5 does. It's a better measurement where we're certain to 2 digits how close that value is. What about the number 0.02080 meters? In this case, the 2 zeros on the left-hand side are not significant. They only tell us it's a small number. But the 2080 contains 4 significant figures that all make it a better measurement. In very large numbers, zeros are sig figs if the number includes a decimal. So if I wanted to write the number 320 grams with different numbers of sig figs, notice 320 means the 0 is not significant. It's just telling us it's a big number. 320 grams tells us that the 0 really means 0. It could be 319, it could be 321, because the last significant figure can always be off a little bit. But it's right on the money. For 4 significant figures, we'd have a 0 after the decimal point. Defined numbers have infinite number of sig figs. Only measurements have significant figures. So if I said, for instance, that 5,280 feet equals 1 mile, that's not a measurement. We're not saying there's 4 sig figs or 1 sig fig for those measurements. It's an infinite number of sig figs because that defines them. For instance, if you said you had 5 fingers on one hand, that doesn't mean, well, there might be 4 or there might be 6. No, there's 5. It's a defined number. We don't use sig figs for defined numbers. Sometimes we have to round numbers, round off or round up. Your data means the experimental measurements you take. The precision that you measure is expensive, and the better your equipment, the more sig figs you get, but the more money you have to pay for it. So remember, record as many sig figs as you can from your data. Your results are what you calculate from your data. You cannot report more sig figs in your results than you can honestly claim, but you want to report as many as you can. So remember these 2 rules. Never round the data you measure. Always round the calculation results that you calculate. Let's look at this example. I've got 2 sets of numbers right here. We're going to round each of them to 5, 4, 3, 2, or 1 sig fig. Here's what happens. You can see that each of the data measurements becomes less precise as we have fewer sig figs. So study this to remember how you're going to round off to the proper number of sig figs. Finally, let's take a look and see how calculations are rounded from the data. Most of the time, we'll multiply or divide data in order to get our calculations. The rule is when you round off answers in multiplication or division, you round them to the same number of sig figs as the data with the least number of sig figs. In example 1 and 2, you can see our calculators would give you these answers, which look fine, but they're wrong. In the first example, you have 3 sig figs in the first data and 2 sig figs in the second. Your answer should have just 2 sig figs. In the second example, you have 3 sig figs in the first data and 3 sig figs in the second data. Your answer should have 3 sig figs. These are what the answers should be rounded off to. Sometimes we'll also add or subtract data in order to come up with the correct answer. Now we don't care about the number of sig figs, we care about the place of the sig figs, of the final sig fig. So in the third example, you'll notice that the first measurement goes 2 places past the decimal, and the second measurement goes 1 place past the decimal. Your calculator gives you 12.54, but that's not correct. We have to round off to the least accurate place, which is the 10ths place. In the fourth example, we can see that when we subtract those two numbers, our calculator gives us a 7. But wait, each of those measurements is accurate to the 10ths of a place. Shouldn't our answer be accurate to the 10ths of a place? Yes. These are what we would really record as our answers.